Right, I should have a pretty interesting video for you guys today, actually. So, as I've said before with the Riot, we did actually quite a lot of computer-based design before we built the first one, um, but there's no substitute for physical testing. So, of course, you do the flight testing, but the other part of that is doing test rig testing, and we think that's a really important thing to do. It's basically it's the best way of testing a glider, and you find out stuff about it that you just couldn't really do in other methods. So yeah, I'm showing you quite a lot of detail here. Now, sort of some people have said, "Oh, perhaps you shouldn't be showing customers all everything behind the scenes." But actually, I think it's really important that basically we're open and that we show everything that we do. And so yeah, it's this video. It spoiler warning, it does contain broken wings, but you find something useful out by doing that process, and ultimately that's why we do it. And I think it's particularly important with this type of wing because these sub 70s, there's not a certificate of airworthiness on any of them as such. It's the pilot's discretion to fly. Like it's basically the pilot making a decision. And so if you're going to fly one of these wings, I think it's really important that you actually see what goes into it. And so yeah, you can see here how we deal with a failure, and in a very literal sense, we come back a few months later stronger. Hi there, so welcome to sunny Yorkshire. We're here testing the Riot wing, and in about an hour from now we should have the wing up on top of this truck here, and we'll be testing it for pitch stability and also for the load it carries. So we're using here is the BHPA's test rig. It's a piece of kit which is built for the purpose of testing hang glider wings. It's basically, as you can see, it's a big Chevy pickup truck with a big thumping V8 engine in it, because actually you need quite a bit of power because we've got to accelerate up to the speed we need to be at to test it. The wing itself is obviously very heavily loaded through some of these tests, so it's putting an awful lot of load through the whole system, drag on the car as well, because when you're at these high angle attacks there's a lot of drag going, so you actually need quite a bit of power to do that. And then of course we've got to stop before we hit the end of the runway as well. So the purpose of this testing is that, as I say, it's twofold. So we're testing the pitch stability of the wing, and we're also testing its load carrying capability. So the reason it's important to test pitch stability on a test rig as opposed to just by test flying it is because it enables us to get into areas of the flight envelope that you would never normally want to be in when you're in the air. Now, the particular case that we're testing for here is at negative angles of attack, or very low, close to zero angles of attack, where the wing is not generating lift or is even generating downforce. So this is basically where you'd go completely straps loose. And because a hang glider or a flex wing microlight are weight shift aircraft, the pilot only has control when he has weight on the wing and when he has weight to move. If he goes weightless, there is literally no control at all. So it's at that point it's completely reliant on the natural stability of the wing. Now, this might only be for a millisecond, but what it needs to do in that moment is to pitch the nose of the wing back up again so that the load is re-established on the wing, and the wing will fly away then normally, and normal controls re-established. That's a pretty extreme situation to get into a negative G situation. It's something which, as I say, you can't really test fly for. It's really only going to be something which happens in pretty extreme turbulence. But it is important to test for that because, as I say, that's the point at which it's the stability of the wing that really becomes critical. The other thing we're seeking to test here is the load carrying capability of the wing. So there's two main ways you can test a wing like this. So the first is we put it on this special test rig, and that's measuring the lift, the drag, and also the moment. So how much pitch moment, how much it's trying to pitch up or pitch down. Obviously for testing the load, it's the lift component we're most interested in, so it's finding how much lift is this wing able to support. So you can do it like this by driving at speeds down the runway and measuring the actual force which is generated by the aerodynamics of the wing generating lift. The other way it can be tested is with a static load test, which is typically putting the wing upside down and piling up sandbags on it. So the advantage of doing it aerodynamically like this is that this is actually a real world test, in that the load distribution is correct. It's the air which is putting the load on the wing, and obviously if you're in the air and you're putting a lot of G-force, it's the air which is putting the load on the wing. When you're choosing how to pile the sandbags up, you have to make certain assumptions with how that lift is generated, basically where you put the sandbags on the wing, and depending on those assumptions it can affect the test. And also, because it's a static test, there's no sort of inherent margin in that test. You know, if it passes that it just supports that load, whereas actually in practice when we test with this way, because we get little gusts of wind, little bumps on the runway, we aim to we get to the load, the maximum load that we're aiming for, but then inevitably you actually, when you look back at the data, because all the data is being logged to a computer from the test, you actually see little spikes. So in fact we're actually it's if anything a slightly conservative test to test it in this way. So the test rig that we're using today, it's the BHPA's test rig. As you can see, it's a big Chevy 7.4 litre with a nitrous injection, even though we probably won't use the nitrous today. It's one of the only ones in the world. It's got this frame on the top which actually mount the hang glider. It measures the load going through it, the lift, the drag, the pitch moments, and all of that data is recorded in real time to the computer, along with the angle of attack measurement and the airspeed that's being measured off the probe in the front as well. So it's a really good bit of kit. It's one of the only ones in the world. We're really lucky because it's actually only about a couple of hours down the road from our factory here, but it's a facility which anybody, any manufacturer can pay the BHPA for the daily rate and come and use this. So it's really important to keep these kind of things running for hang gliding and for the new sub 70 trikes as well.
So something I should point out at this point is that actually test rig days are pretty damn stressful. So it might not quite appear it in the video, but there's a lot riding on these days, because you're taking this wing that you've been working on for ages. It's the first prototype of it probably that you're taking there, and you find out whether it's working or not, for one thing. So of course your best case scenario is that you come away from the day and your wing's still in one piece and you've got all the data you need and it's all what you hope for. Now if you break the wing on the test rig, obviously that's not what you want, but at the same time, as long as you've learned something from it, then it's not a disaster. Of course the big disaster would be if you were to break the wing and you didn't capture the data that you need. So there's always quite a lot of time that's spent at the beginning of the day making sure you've got everything completely right. So you winch the wing up onto the rig, spin it round, attach it all on, check all systems are working fine. Sometimes, because the rig doesn't get used very often, you sometimes have to clean a few contacts out and make sure you're getting good data out of everything. The weight of the wing is measured on the load cell, so everything's zeroed. The centre of gravity of the wing as well is found relative to the hang point, and all these parameters need to be set before you start. And then also you're trying to capture some videos, so you're trying to get some GoPros mounted around. Unfortunately we didn't get as much GoPro footage as we hoped for from these runs, but we did get good data. So you drive out to the runway, and obviously we've got permission for the data to be used in the runway then, but it is still an active airfield and there's aircraft taking off and landing, so you do have to keep good lookout for those, and we're on the radio, so we're listening in on the radio and also calling what we're doing each time we're starting a run. We radio in that we're doing it. So the first thing you can do is you do the stability runs. You get that data in the bag first before you start seriously loading up the airframe. They're done at a series of speeds. So although the sub 70 microlight wings, there isn't a certificate of airworthiness as such. We are following basically as close as we can to the BHPA's hang glider type certification process. So we're testing it at the same speeds that it would be tested as a hang glider, because ultimately these are powered hang gliders according to, well, legally, and also in terms of the ways they fly as well. So we test at the speed range that we'd be testing the hang glider wing at. So you start off at 32 kilometres an hour, then you do a run at 48 kilometres an hour, then I think it's 64, and then there's a final one at 96 kilometres an hour. So you run across a pretty wide speed range, and you're running the range of angles of attack across there, and you're measuring the forces and the resulting moment. And the most interesting thing there is the moment, and making sure that it's pitch stable. Unfortunately, the GoPro footage ran out just after the first pitch run, so we only got a very low speed, fairly unexciting run recorded on that GoPro. If you look inside the cab of the truck, you can see that we've got our laptop plugged in there, so that's recording data live, and I'm adjusting the angle of attack in real time as we're going along. So I'm trying to control the angle of attack so that we can capture the full range of angles before we run out of runway. So that's you're trying to adjust that speed and trying to make sure you get all the data caught before you get to the end of the runway. We're doing all the runs into wind, of course, or as close as we can. We usually go a bit diagonal across the runway if we have to just try and get as much into wind as we can. After you've got all the stability data, and this worked really well, so we didn't have any issues with it. We actually, for the purposes of this test, we were looking to test a different luff line arrangement. So we had the option to fit an extra luff line if we needed it, and we didn't. It passed fine with just 2 luff lines on each side, which was really good news, because that then opened up the possibility to being able to fold it on the trike. We weren't sure if we were going to be able to do that, so we found that out. So that was really good. And then once you've done the stability test, then it's time to start pushing it a bit harder, and you start loads testing it. And unfortunately, this is where we had a problem, as you're going to see just now. This wasn't supposed to happen. Let's just have a watch.
So it's the end of the first day of testing the Riot today. Not entirely the results we were hoping for. We passed the pitch test, which is good news, of course. On the loads test, we broke the wing at just over 760 kilograms of load. So if you divide that by 6 to account for the 6G, that's only giving us about 127 kilograms as that it passes to, which isn't really enough. So we're going to have to reinforce the cross tubes, which is the point that broke. We'll add extra sleeving into those cross tubes, and have to come back for another day of testing then, which is a little annoying, but that's unfortunately the cost of price of trying to develop a new wing.
So what happened there? Well, obviously we broke the glider, but at the end of the day, that is why you do the testing. It's to find that sort of stuff out, and we did gather data logger running. We got good data from that test, and so we learnt something. So the bit that failed there, you could see it in the photo. It was a cross tube that broke. It broke pretty much in the middle, which is sort of where you'd expect, because what you've basically got with a cross tube is my demo piece of spaghetti here. It's a long thin beam that's loaded in compression, so the critical load case here is oiler buckling. Now theoretically that cross tube should have been strong enough for more load than what it actually failed at, but the problem is, what you can see is you can put quite a bit. I'm squeezing this spaghetti quite hard now, it's pressing into my fingers and it's standing the load, but what happens is when I put a little bit of side force onto it, it goes. And that's basically what was happening there, because you got a double surface wing. So if it had been a single surface, it might not have gone at that load. But with the double surface, you have the undersurface, which is pressing up onto the cross tube. We can see little sort of marks from the on the batten pocket from pressing on the cross tube, and that was at about the point where it actually went. So we're pretty sure that side loading was reducing the amount of compression that the cross tube could take. So as I said in the video there, actually the solution to that is fairly simple. It's just that you need to reinforce the cross tube. So a piece of sleeving in the middle of the cross tube, because that's where you need to stiffen it to resist that buckling load. It doesn't add too much weight actually, less than a kilo. So the Riot's still one of the lightest sub 70s around. It just means that then obviously we've got to rebuild the wing. We actually did the next test with a new sail as well, because we wanted to just tweak some sail cut changes as well. So we reran the pitch tests as a result of that. Unfortunately, it takes quite a while to get the availability of you've got to have availability of the airfield, you've got to have availability of the people to run the rig, and you've got to have decent weather as well to do it. So it took us a while before we got back to the test rig, but we did, and you'll see that now.
Hi there, so we're back at Roughworth again. Reinforce the wing a little bit, and going to try the load test again, and also this time making sure that we're actually getting the data out of the maximum lift to drag ratio.
Unfortunately, we didn't get brilliant video from this day. So you can see that I've mounted the GoPro in a different position on the front of the truck. I thought this might work quite well looking up at the wing, but it really doesn't. You can see here we're not really seeing very much that's particularly useful or interesting. Also, we didn't have anyone to stand outside and film, and the drone wasn't there this time either to film us. So yeah, and that's a shame, because when you look at it from the outside, you can really get an impression for how brutal this test is. It's really quite hard on the glider. So what you're seeing now is a Fly 17 being tested on a previous go, and yeah, you can see it's really working the glider very hard, distorting it very hard. We did get some video from inside the truck. Again, I was hoping this sort of might capture the drama a bit more, but it looks a lot tamer on the camera than it felt in reality, because you're sort of having to thread this truck between the hay bales, which were there this time, to try and get as maximum length of run that you can, or go around the corner onto the runway, carrying a bit of speed onto it. We're trying everything just to get as much speed up as we could, and really try and work this glider as hard, or work this wing as hard as we could. So yeah, I'll just let a couple of runs play for a moment and hopefully give some kind of impression. And you can see we were stopping pretty close to the end of the runway on some of those occasions. I think probably the driver could have braked a little bit harder, but if he'd had to, but we were pretty close to the limit actually, and yeah, it was certainly foot flat to the floor. All of that American V8 muscle trying to do its best, or trying to do its worst, I should say.
No load yet.
That should be, if that exceeds the negative load, then we just
Here
don't
we go,
test.
96, it's right over there. Well, I'll worry about that once I've got through the gap. So good so far. So far so good.
Okay, so back at Rotherham again, and it's the end of the day, and as you can see, we've ended the day with a fully intact wing, which is always a relief. It's always good news. So we reran all the pitch tests just because there's been a few tweaks to the spec since then. So that was all fine. Then we started ramping up the load, trying to get the load. So we were trying to work out which was the better runway to use, because we kind of had the option between using a shorter runway, which was into wind, not that there's a lot of wind today, or we had a longer runway which was crosswind, and also meant negotiating a gap through some straw bales at the start to try and get as long a run onto it as possible. So basically we were kind of pushing the envelope of what this thing can do. So 5.7 litre V8, but as you can see it's also quite heavy, and when it's got that amount of drag off the back of it as well, and the nitrous kit isn't in action at the moment. So basically we've been running this thing flat out, and as you can see we haven't broken it. We didn't get quite as much load on it as I was aiming for. I need to run the data later and check what number we actually got out of it, but it was definitely well over the 6 times 120 figure. So that's yeah, I think we probably saw about 780. Maybe we might have just peaked at about 800, but as I say, I'll look at the data later and find out what we actually got out of it. But the interesting thing was, I think it would be very difficult to actually get much more out of it, because you get to a point where you can't increase the angle of attack any further, because you just start pouring drag onto it, and because the drag doesn't count towards this way of testing it, that doesn't get you a higher figure. And also it seems like even going faster wasn't increasing the load in the rate that you'd expect, which I think is the nature of a flex wing hang glider type wing, in that as it loads up more, it also releases the load. So it actually seems like you can't get it to that higher load using this method. But then that's also realistic, because when you're in the air, it also means you won't get it to those kind of loads.
So when I got back, of course, the first thing to do was to download the data and crunch all the numbers and see what we've actually got. And actually, it turns out we did better than I realised at the time. So we did actually get pretty high load on that wing, and so I'll show you the data now. But there's a sort of few things to bear in mind first. So when you do a sandbag test, another thing about that is that you turn the glider upside down, or the wing upside down, load all the sandbags onto it. So you just bring one single load onto it, which is probably going to be at 90 degrees to the keel. Now, when it's on the truck, your aerodynamic load, of course, is applied across the whole thing, but you can think of that also as being a single aerodynamic load. It simplifies down to that. But for the purposes of the test, we split that into the lift and the drag components, so the vertical and horizontal component. And then the drag doesn't actually get counted towards the number that we're quoting. We're just quoting the vertical bit of that load. So what that means is that if you tilt the wing too far, so you go well past the stall, you start putting drag on the wing, you're adding more and more drag to it, but it's not actually giving you any more lift, so it's not giving you that number that you're looking for. So what you're trying to do instead is to put it at the peak lift to drag ratio, and if you start going past that point, you're just going to start adding drag to the wing, which is real force that the wing is really seeing, but it's not registered as part of the test. So that's another reason that a test rig truck test like this is harsher than the sandbag test, because whereas with the sandbag test you're counting all of the weight you're putting on it, with this truck test we're only counting the vertical part of the weight that we're putting on it. A neat thing that I mentioned briefly earlier about flex wings, and this applies to all flex wings to some extent, is that they do something called load shedding. So that's where, as you're trying to put more load onto it by either increasing the angle or by increasing the speed, they tend to twist and deform more in the direction that actually releases load from the structure. So whereas for more rigid aircraft, the kind of 3-axis type aircraft, they can be overloaded by doing violent manoeuvres, with a flex wing it tends to be that as you do these manoeuvres, it tends to deflect in a way that actually reduces the load that the structure sees. So from the point of view of trying to get the load onto that for the test and get a bigger number as we can on the test, this means that it makes it difficult to do. What it actually means is that in the air, the same thing will be happening as is happening in the test, and it will tend to mean that the load that the structure sees isn't as much as it would otherwise being. Now, obviously, this isn't an excuse to go out and start doing radical aerobatics and try to demonstrate this, but it is something which is sort of to bear in mind. So now, if we look at the data again in detail, on the positive load case, so on the plus 6G load case, we actually managed to get to 864 kilos as the peak load recorded. So divide that by 6 and you've got 144 kilos. And also you can see from the graph that actually the peak there was actually relatively early in the run. So what I was doing is I was increasing the angle of attack. So we accelerated the truck up. We got to, it felt like it was sort of getting towards its top speed, so that then I increased the angle of attack at that point up to first off up to about 20 degrees, and that's where we got our peak load. Now I carried on trying to increase it further, trying to get more load onto it, but actually you can see that the load plateaued and even started to slightly fall after that, and the truck wasn't getting any quicker either. It was basically, well, it's foot to the floor, but it was the wing was holding back the truck at that point. It simply couldn't accelerate anymore. So so though the drag was increasing, we weren't getting any more load. We weren't getting any more lift being applied to it. But we got our peak load out of it though. So it was a really successful test, and the wing survived that. And as I say, I think in practice what this data is actually telling us is that even if you tried to put the 6G onto it, and of course this isn't an objective for anybody, but it looks like it would be very difficult to actually put those kind of loads onto it in the air, and that even if you did manage to do that, you wouldn't break it. So that's the outcome of the test, and that was a very successful day at the end of that, after our initial disappointment. So going with the computer simulation, which we've already done, and the flight testing, which we've done, and now the physical test, which, as you can see, is a really pretty brutal test, we can say that this is now a really, really well tested wing.